Thank you very much for that introduction. OK, so yesterday we've seen Squib and we've seen Showtime, so different types of side channel attacks, and also a way how to amplify that leakage. And now we want to continue this discovery of microarchitectural attacks. And why do we want to do that? Is that even relevant? Yeah, it actually turns out it is. So 5 years ago, we've seen headlines like these. And maybe some of you still remember those. It turns out microarchitectural attacks can actually have a huge impact on the security of our systems. And here specifically, we saw the impact of 2 attacks named Meltdown and Spectre. Then over the years, so 5 years ago to today, we've seen lots of different new variants of such attacks. And today, we're going to discuss those attacks, but also some other related attacks. So in general, we're talking about microarchitectural attacks here. And more specifically, we take a look at how they actually work and how we can find them in an efficient way. But to also, again, introduce us to, my name is Daniel. I'm a PhD student for the CISPA Center for Information Security, and I'm working on detecting such attacks. I'm also not alone here today.
Yes, so my name is Schwarz. I'm also working at CISPA. So Daniel is my PhD here, and we are trying to find all the problems, destroy all the things, and then fix them, of course, to make everything a more secure world. And obviously, it's not just us two. So all these things we present today, they involve entire teams. So all this research that we summarize here and show the interesting parts, they involved a lot of people, as you can see here. So let's think about a CPU first. If you think about a CPU, and for us, it's mostly a black box. So it's something we have in our computers, we run some code, it does something. If we adhere to the specification. So all the CPUs we have, they come with some manual, some specification, an ISA that defines what we can actually do on a CPU. So they define like which instructions do we have, what registers can we use, how does the memory work, and then we write our applications in a way that adheres to this ISA. And that's how we interact with a CPU. So this is pretty nice because this is standardized and we can just rely on that. And normally, everything works as expected. So if we write our code, if we do exactly as stated by the manual, then we have our applications that run on the computer. And also in this talk, we assume like all these bugs that we have seen that are everywhere in software, we assume we don't have them. So our systems that we look at, we have the assumption, okay, all these software bugs, they are easy to fix. I mean, we have seen it's not true. Even very simple ones that we know for decades, we still have them. But let's assume we don't have any bugs here. And then this question arises, can we still attack our systems? Can we do that in a nice way? Can we actually leak some information without exploiting any bugs in the software?
Well, actually, I think we can. And we've also seen that yesterday. So information in our microarchitectures and our CPUs, that can leak through side channels or side effects. And what are those side effects? So yesterday, we've seen a few, but there are various types of side effects. So for example, power consumption, or even the temperature of a CPU. If it's actually in use, it's a little bit hotter. So it will then essentially be cooled down again, and we can actually measure that. And also execution time. We've seen that can also be amplified. So all these things, they somehow convey information.
So there are a lot of side effects that we can observe, and we've seen that, well, yesterday, that we can look at them. So basically, what we have to do if we work in microarchitectures, it's very simple. So we have a device, every device has side effects, so we just observe it. And I mean, we have seen that impressive demo yesterday. We can do that just by looking at it, and then we see the side effects. Then we evaluate what we see, and then we get the secrets out of that. Well, it's pretty easy, right? So we basically chose the simplest research direction in security.
Yeah, like, honestly, I tend to disagree there a little bit. Like, the reality is not as easy. And why is that? Well, temperature, okay, I can feel if something is hot or cold, but measuring that, okay, yeah, maybe there are ways, but we want to restrict ourselves on software-only attacks. So everything that we have are software-accessible interfaces on a CPU. And what does it mean now for us? As a result, well, we have to understand the inner workings of a CPU. And we've also seen that on this very detailed looks into the microarchitecture yesterday. So we really need to get our hands a little bit dirty there.
So what you want to say is that we actually need to know first what we can observe, how we can observe it, and then we additionally have to understand how a CPU works internally as well. Okay, well, then it might not be as easy as expected.
Okay, but
maybe you have some insights on that.
Yeah, I think we'll get there. So let's start simple. As I already said, we start with some interaction with our CPU, and we do so by obeying to the so-called ISA, the instruction set architecture. Well-known examples for that are, for example, x86 or Spark or ARM. Okay, that defines somehow what we can execute. And basically, that's just our interface to our actual hardware. Okay, the microarchitecture, so microarchitectural attacks, they all rely on some fancy word that is the microarchitecture. It's just a word to describe the implementation of this ISA. So how CPU vendors came up with smart ways of actually implementing the x86 instruction set, for example. So that's our implementation there. And maybe you've also recognized some of those logos, like common names that are, for example, the Skylake architecture or the Zen Freeze and Plus architectures, and so on. Okay. So, but what does it mean now? Well, typically, modern CPUs contain lots and lots of different microarchitectural components, and they all interact with each other. But luckily, they're transparent for us as programmers. So if I write a program, let's say Hello World or even something more complex, I don't really care whether the program is executed on my Intel laptop or on an AMD laptop, or like those are all the things that are transparent for me. Okay, that's neat, but it's also really cool because CPU vendors are now free to optimize for different types of things like performance or just the power consumption on my laptop battery. And they can do so because as long as they implement the ISA, we're fine. And we want to go through some of those optimizations today, and we'll also see how we can attack them. One optimization that you also saw yesterday is the CPU cache. So we want to recap that shortly again. Basically, suppose you have two memory accesses, and in the middle you have your CPU cache. On your right-hand side, you have your main memory. The first CPU, or the first memory access here is what we refer to as a cache miss. Because our cache state, well, everything is still empty, so we just fetch that from DRAM. Okay, at some point we get the response. Now we just put that into our CPU cache. That's cool now. We've also seen that we can now access that very fast. So our second access here, cache hit, can be served directly from the CPU cache instead of going again to the DRAM, and that's cool. Why? Because the first access was really slow, the second access is way faster. And while you can observe that with your own eyes, if you really, really take a lot of work to amplify that leakage, you can also measure that with very precise timers, and then you end up with a diagram roughly like this.
I mean, that's nice. That's how it's designed. Those like the timing differences we should see. We have to make things faster, and that's great. But it turned out that this can also be a security problem. So a well-known attack based on these timing differences is flush and reload. And for flush and reload, simplified illustrated here, we have two processes, an attacker, a victim, and they share some memory. Could be a shared library, for example, with some math functions, crypto functions. And the nice thing about shared memory is, if it is cached, so if one process accesses it, put it in the cache, it's cached for all the processes. So how does the attack work? So basic idea is the attacker flushes the shared memory from the cache, so it's not cached anymore, it's only in the DRAM, then waits for the victim's turn. The victim might now access the shared data. If the victim does so, then, well, it will be cached. We've just seen that. That happens automatically. It's in the cache. And then the attacker's turn, the attacker can simply access that shared memory and time how long it takes to access it. So if that was accessed by the victim, it's in the cache. Accesses are fast. If it was not accessed by the victim, it's not in the cache, it has to be fetched from DRAM, and this is way slower. So with that primitive, we can see if a part of the memory was accessed by someone else or not. So it's already something where it's like, okay, cool, kind of. This can be a huge security problem if you have memory accesses that depend on secrets. And we have seen that in old cryptographic implementations where the memory accesses depend on the secrets of the secret key. But it can also be used to transfer information between, for example, virtual machines, or just monitor function calls of different applications, building communication channels between applications.
Okay, but that's basically just the leakage of 1 or 2 instructions here, so that's very, very specific, right? But the x86 instruction set is huge. So depending on how you count, you have over 3,000 instructions there. So I wonder, okay, we've seen the results of that research, but let's get one step back. How do we start something like this? How do we even find such attacks?
Well, we have seen that yesterday, right? I mean, there's always like one PhD student at least involved, and one PhD student can look at one thing. Then we have 3,000 instructions, we get 3,000 PhD students, and they find all the attacks. We just let them sit there the entire day, read documents, read patents, and they have a lot of time. I mean, you can do one of that. And maybe by reading these 5,000 pages manuals and thousands of patents, they develop some ideas, they try something, test the ideas, and in most cases, from my experience, have to start over and do that again because it did not work out and there was no security problem there. So we could do that, right? I mean, we could get an infinite number of PhDs for that because it's not over with the few thousand instructions you mentioned, because we get new CPUs every year with new features. And so we can repeat the entire process every year again and again. So we create infinite number of jobs. It's great, right?
Like, to be honest, don't take it the wrong way, but I like my weekends. So I really, that's not the way here. Like finding side channels, that's complex, time-consuming, but I don't want to end up like this.
Okay, but then you have to provide me an alternative. So can we do better than that?
I'm not sure, but let's try to figure that out. Because back in university, I attended some classes about software security, and there we have better ways, right? Like software security, we can just apply a technique called fuzzing, and fuzzing is just you automatically generate lots of invalid, malformed, maybe weird or maybe valid input. You just throw that into your program, and then maybe it crashes. And if it crashes, like your browser engine, maybe you found a seg fault, maybe you found a bug. So can we not do the same thing here? Can we just not fuzz side channels?
So I like the idea, yeah. I mean, I always like to let the computer do the things that I don't have to do them. But it works well for software. Yes, that's true. But for software, we also have a lot of feedback. So for software, yes, it crashes. A CPU, crashing in a CPU, that's not something that we see regularly. A software might do different things depending on the input. It's also hard to see. Also, for fuzzing, we typically need some form of instrumentation so that we see where we are, what we already covered. And this is really difficult in a CPU because we cannot add probes into the CPU. So if you try that, yes, maybe, but we have extremely limited feedback. And it's not the only problem we have. So for software, yes, we crash it, we start it again, it has a clean state, and we can do the same things over and over again. On a CPU, we have a lot of states, and it's not easy to reset a CPU to a known clean state. That's not only because we had to reboot it for that, but also there are many, many things running on the system. It's not only our test application, but there's an operating system, there are drivers involved, interrupts for the communication with the devices. So everything changes the state, the internal state of the CPU, and getting a clean state, that's really difficult. And as all these applications influence the state of the CPU, that also gives us a lot of noise. So sometimes we see something, but we don't know, is it from our input? Is it from someone else's input? Is it a combination of the input? So there's a lot of noise involved, so that makes it pretty difficult because we don't have this nice setup that we have in software. And even if it's like we can solve that, that's just engineering, to some extent. There's still one thing that you need to solve for that.
What is it?
How do we even decide whether we found a side channel? Yes, an application crashes, but here we have some timing differences of some execution, for example. How would we even know that there is something like that? So it is not easy.
Okay, it's maybe not easy, yeah, I get that, but it sounds more promising to me than just looking through 3,000 instructions. So let's give it a try. If I now think about side channels, like on a very abstract level, I come up with those two things, like ones and zeros. That's what we're all about, right? So let's define that as some cold and some hot state. Why do we do so? Well, if we can encode something in some arbitrary state, and we can encode a 0 and a 1, we just do that multiple times, and we can encode arbitrary information. So far, so good. Now, how do we get an interaction with that state? Well, let's say we have some instructions that we execute, and they reset our state to our always 0 state. Okay, we execute them, we're back in our 0 state. So far, so good. Naturally, we also need some code to execute to end up in the other state. Okay. Now, what we're still missing, because we can now encode something, we still need to receive that information again. And we've seen that by just timing the execution time of some instructions, you sometimes get data back. So let's just do that. We call that measurement, because this time we just measure the execution time of our instructions, and maybe we get something back. Maybe we find some instructions that obey exactly this pattern. So the idea here is, when we have this in mind, we can actually find out whether given arbitrary code sequences, whether they behave like that or not. For that, let's just start executing them. So for the first case, we reset everything, we measure it. According to our definition, we should end up with our 0 state. Okay, then we do the same thing again, but this time we trigger a state change to our 1 state. So according to our definition, we would end up in another state. Okay, and now I claim, if you can distinguish those 2 states, you actually found a side channel. And doesn't that work?
That sounds very theoretic. Can you maybe give me an example of that so that I have an idea what you're talking about?
Okay, fair enough. So let's take an example for that. Very simple one. We take the x86 instruction inc of a memory address. All that it does, it reads the memory address, thereby it puts the memory into the CPU cache, increments the value by run, and writes it's back. But everything we care about here is it puts something into the CPU cache. So if we execute that for sequences here, we basically have 2 assembly instructions after one. We time the execution time of the second one. The first one puts the memory into the CPU cache. The second one accesses the now cached memory. We've seen that's very fast. On the other end, we just do the same thing twice. We measure the execution time of the third one. Still very fast. Okay, so that's not really surprising. I have to admit
It's not a side channel.
Yes, that's actually not a side channel. But if we have one minor modification here, so just one of those sequences, we change to the CL flush instruction, which is the x86 instruction that just removes a given memory address from the CPU cache. So what happens then? Well, first off, we remove the memory address from the CPU cache, and then we load it. So that's now a cache miss. We've seen that. That's very slow. On the other hand, what happens for our second case now? Well, we remove it from the memory, we bring it back to the memory, then we time the access. Well, but it's back in the CPU cache now. So that's now very fast. And that's actually distinguishable now. And one is very slow, one is very fast. That's now a side channel.
I also recognize that. That's basically flush and reload that you showed as an example here.
Yes, exactly. Because by just executing or not executing this trigger sequence, I can just encode information. And with that in mind, I claim we can just start fuzzing for CPU side channels. Okay, we start very simple. We get a list of all instructions. Then we just put them into the form of our model that we just defined. So we just take always 3 of them, take all permutations. OK, so far so good. Then we just execute them. And we do so in exactly the same manner we've seen on the previous slide. So we just test whether they obey our definition of a side channel or not. Well, if they do, then there's still these noisy things going on a CPU. So we just try that all over again, re-randomize our execution patterns a little bit. And then we'll end up with a good approximation of which results work and which won't. And then one last step, because we end up with a few thousand of results. And yes, I like my weekends. So we just cluster them together. And then it's easier to read through them. OK, and the end result is then just some report that you can investigate. Take a look at the results you got there.
So that doesn't even sound good in theory. That actually works. So Daniel built that. And we let that run for 4 days on different machines. And that really rediscovered some known side channels, which means like, well, reproducing existing stuff. Everybody can do that. But it also found completely new side channels. So in 4 days, we found 4 new side channels. So you can extrapolate that. So we are done in 10 years. And then we found everything. And these are not only useless side channels, where say, okay, something does something. We actually showed that, well, we can build new attacks based on the new side channels that we discovered here. So what is this new attack that we also brought here with us that we can build using the side channels? It's a break of kernel address space layout randomization. So what is this about? You have your operating system, and there are always attacks against the operating systems. And these attacks, they typically need to know the exact location in virtual memory where the kernel is stored. So to make them a bit harder, operating systems move them around. So with every boot, they are at a different location. So it's not easy to know where they are. And if the attacker doesn't know where your operating system is, then it's a bit harder to attack it. So if you look at the memory layout after boot, after every boot, your operating system is in a different part of the virtual memory. And, well, to make attacks reliable again, normal attacks, then you need some way of figuring out where your operating system is located. And that's exactly what we can do with one of our attacks, the flush and conflict attack, that builds a new KSLR break based on a side effect of the non-temporal move instruction here. And this is pretty nice. So we have seen a lot of KSLR breaks, but many of them get fixed over time. This one is a very cool one that even works up to the newest CPU generation that we have tested. And it's also extremely reliable and fast. It's just a few milliseconds that it takes to actually de-randomize the location. And you can give some more details how it works, right?
Yes. So if you just play around with the instructions that Osiris output, then you can come up with something like this. So once again, you see this 3-phase approach, or 3 different types of sequences. And we use the exact same thing here with a little bit of manual work for the following setup. So on the left-hand side, you see possible locations of the Linux kernel. So in blue, the actual location of the kernel is marked. Those are 3 locations. That's where no kernel resides. On the right-hand side, there's just some memory address. OK, and we start by just executing the CLFlush instruction and flushing that green memory address. And afterwards, we access, with our non-temporal move, some address where we hope that the kernel is there. We do not know that yet. And afterward, we just execute a load on the green memory address. And the thing here is that this move will fault. Because we're in user space, we do not have the privileges to access the kernel. Neither we have the privileges to access something that doesn't even exist. So that will always fault. But depending on whether the kernel is there or not, this load is executed or not. Well, that happens transiently, but we can still observe that. We just take a look whether the green memory address is cached or not. If the kernel is not there, then it's actually cached. If the kernel is there, then we do not see a cache hit, but we instead get a cache miss. And, well, same thing again. If the kernel is not there, we see a cache hit. But that's still a little bit theoretical.
So we promised the people here that it's fast and reliable, so maybe we do a live demo, right?
We can try.
Can we do a live demo?
Yeah.
Let's see if the demo gods are on our side.
Because the thing is, like, if I really want to play around with memory corruptions in my operating system now, it's as simple as just compiling the code and executing it. Okay,
That's
so
it.
we get some address. And we can also check whether that's the correct address. So if we use root privileges, we can actually check the location. There we see those two addresses match. So by just executing a simple code snippet and wasting 144,000 microseconds, so basically nothing, we can just de-randomize the kernel location.
So that completely breaks this mitigation.
Yeah, at least up to every CPU that Intel brought out so far. Okay, that's cool. But to get back to more an educational perspective, like, what do we learn here? Like, we've seen these things, we can automate stuff. So first reason, okay, we can automatically search for side channels. But to be honest, scaling such tools is still challenging, and our current prototype is limited to one instruction per sequence. So while we found a few side channels there, we cannot find everything. So side channels that we've seen yesterday, they're too complex to be found by our current prototype.
And there's another limitation with that approach. I mean, that's side channel information. It's nice. I mean, we've seen a lot of side channels and that they impact the security of systems, but there are still side effects. And many people's like, well, just write your software in a way that you don't have side channels and everything is fine. So maybe we can also have ways of finding more powerful attacks. So I'm talking about microarchitectural attacks that really leak data. So not only metadata, so information about data, but the real actual data. So I'm thinking about something like Meltdown. So Meltdown is also a microarchitectural attack. It exploits out-of-order execution and with lazy error handling so that you can already get some inaccessible data for a short period of time during this transient execution and then combine that with a side channel to make it architecturally visible. And that would be pretty nice to also find these things in an automated way. So far, everybody did that manually. So there were attacks like started with Meltdown and Fallout, Zombie, Crosstalk, many, many more. And there was typically one PhD student trying things and then coming up with one of the attacks. But we know PhD students do not scale as well as programs. So we might also want to automate that. And if we look at that from a high-level perspective, it's basically always the same thing. So all these Meltdown-type attacks, they have like one line of code in there where they try to load data from an address that is not accessible. And that will lead to a fault. So at this point, architecturally, your application crashes. But with this out-of-order execution and the lazy permission checks, in that there are more instructions after that, that can still use the value that you're not allowed to load. And they can use that for something like for accessing memory that depends on the secret value you load. So the next line is typically something like this indirection here, where we get this secret value, access a memory location based on the secret value. So for every different secret value, we access a different memory location. Then this will be cached. And then we can use our favorite cache side channel like flush and reload to see what is cached, and from that infer the actual secret value. So they are all like that. They just read data from different buffers and use like different faults.
And you know what? I actually like that idea because there are different possibilities for faults and also microcode assists, so situations that are so complex that the CPU has to take some extra steps to handle the error. And in fact, it looks similar to this. So deciding on whether or not a memory access is valid or not, that's really, really complicated with lots and lots of different invariations there.
But that basically screams for fuzzing, right? I mean, we have so many combinations that we can basically use as an input there for the address. And we don't want to try all the combinations manually. So, well, I would say, like, let's fuzz for these Meltdown-type attacks. And that also works. So the idea is, and this is again a very basic idea, we build some very simple dumb fuzzer that starts with an initial seed of existing attacks and other instructions, unrelated instructions. And then it simply starts mutating already existing attacks with new instructions and comes up with some code sequences. Many of them will not work, many of them will crash, but we still try to execute all these generated code sequences. And we look at them and see if there is some leakage. Do they output some data? If there's nothing, well, in most cases there's nothing, then we go back to step 1, mutate more, add more randomness, generate more random code, and see if something happens. If there is some data that we do not expect that this code sequence would generate, then that's interesting. Then we have to take a closer look. We can also do that in an automated way, and we try to classify that. So we execute that code sequence many, many times, see using performance counters which parts of the CPU are involved in that, so it gives us already a hint, and also see what data we leak. So we can put different types of data in different buffers of the CPU and see what we get. So then we already have some insights into where we leak data from and if this is something that's only stored in the internal state. And this is it's very simple.
Yeah, it seems very simple, but let's see where it really works. So let's say we execute that for a typical working day, so 26 hours. And we figure out, you find around 100 unique different leakage patterns. So yeah, okay, what does that mean now? Well, the more interesting founds are there. Well, 7 attacks, we could reproduce 7 different attacks, okay? So we can find what we already knew.
But to be fair, they are in the initial seed, so.
Yeah, right. But there's also one completely new vulnerability. And what is also interesting, one regression bug. So a bug that was claimed to be fixed, and then in later versions, it's there again. So that's cool. And if we take a closer look into that, well, the new attack was a variant of the so-called zombie load attack. And what happened there? Well, zombie load leaks from some component called the line fill buffer. In this case, we had data leakage from the right combining buffer. Okay, that's some technical terms. What does it even mean? Well, this buffer is used for very fast memory copies, as they're used in OpenSSL or the Linux kernel. And okay, what can we do with that? Well, it turns out you can just leak a complete RSA key while it is decoded in OpenSSL just from another process by just reading thin air, basically. Just read folding memory access, and you get an entire private key. That's kind of cool. Okay, the regression bug, what happened there? Well, Intel claimed that back then, new Ice Lake CPUs were MDS resistant. MDS, being a variant of Meltdown, means they're not affected anymore by those Meltdown-type attacks. Okay, it turns out Transynther just modified 1 or 2 lines of code, and the exploit worked again. So just a simple variant of the attack. Now it works again. Okay. So what do we take from this tool? I'd say the simple thing first, we can automatically search for even more complex variants of attacks, like those transient execution attacks, Meltdown-style attacks. That works. And to some extent, we can also analyze what we got there. Like we can try to classify it into different variants. May not be perfect, but it's at least better than, what did you say, 3,000 PhD students? They're like, come on. Okay, and we can find regression bugs. That's nice, because that means every time a new CPU gets out, we can just take our tools, execute them on there, and we'll just check whether things got worse.
But there will still be people saying, well, that's all side-channel microarchitecture. What about architectural bugs? So things that we can really directly see without involving all the side channels. So maybe on a CPU, it has a manual, but maybe not everything is documented. Could we also find something like unknown instructions that have some security side effects?
Okay. To be honest, I have to stop you right there. Unknown instructions, that was already a thing.
Oh.
So Christopher Thomas wrote Transynther, and there he created a tool that actually searches for undocumented instructions by abusing a trick of the internal working of page faults and the decoder pipeline. There was also RuhrSec, who's a tool that abuses transient execution to again search for undocumented instructions.
But that was just an example. I'm pretty sure there's more left. So if you paid attention in my lectures, there's more in a CPU than instructions.
Okay, yeah, Yeah. We like abbreviations, right? So MSRs, that's something I remember from the lecture. So-called model-specific registers. They're basically just fancy CPU knobs that you can turn and by that configure what the CPU is actually doing. They behave like registers. You can write some value in them or you can just read them and get some value back. Reading value makes sense because sometimes they're used to expose internal information like the CPU temperature. On the other hand, writing values makes also sense because some of them can be used to reconfigure things like enable or disable features. And they're also security critical because Christopher Thomas, the Transynther guy again, he found a backdoor hidden behind an undocumented bit of such an MSRs. So on the VIA C3 CPU, they were really, really security critical. Okay, so let's just search for undocumented MSRs. And we can just start easy. We just scan the entire documented possible range of MSRs. Everywhere where an MSR could be, we just check whether there is one. If we can read or write to that without getting a fault, we do not know what there is, but something is there. Okay, then we reboot the machine, and we tweak some BIOS configurations. And we do the same thing all over again. We hereby check for deltas. So deltas meaning some BIOS configuration enabled or disabled the access to some MSR. And now we end up with a list of lots and lots of MSRs. So naturally, the first thing we do is we split them into documented, so the boring ones, and the undocumented MSRs. So that's the really cool stuff. Then we split them again into different categories, the dynamic MSRs. They change their behavior or their value on their own. So probably they expose some information like temperature or something. And the static MSRs. They do not change their value, so we can probably use them to reconfigure something. Okay, for the dynamic MSRs, we just read out their value and try to correlate it with what we already have. Maybe they're just a second way to access the same interface. On the other hand, for the static MSRs, we just play around with some of those bits, then we execute some instructions, and we take a look whether we can detect any differences there.
And we expect that there are like a few hundred documented ones. There might be a handful of undocumented ones. And when we actually started that, we found there are more undocumented ones than documented ones, so in a range of thousands of them. And some of them, we still have no idea what they are. But for some, we could figure out what they can do. And it turned out there were quite some interesting results there. So some of these MSRs can be used to mitigate existing attacks by accident, basically. So they are good for security. Others, we found one, for example, that allows to introduce new vulnerabilities. So this is not good for security. And some give us already a view into the future. So some of these MSRs hint towards vulnerabilities because they were not documented when we found them, but they were later on documented as being a mitigation for an undisclosed CPU vulnerability. So attackers can already scan that before, see the mitigation, can play around with the mitigation. If they figure out what the mitigation does, it might also be possible to figure out what the attack does. So this is already quite an interesting result. And for the mitigations, we also tried that, and we've seen we can get rid of entire attacks like prefetches that we have seen yesterday. We can reduce leakage for crosstalk or Medusa. So this is quite nice, although it's not easy. I mean, there's still a lot of undocumented stuff. We have no idea, but we can show that this can be automated to some extent to find undocumented behavior and trace changes between releases here. Now it stops.
Okay, so let's conclude on what we've seen today. Basically, we've seen we can automate side channel discovery, we can automate transient execution attack discovery, so Meltdown and friends. And we can also automate detection of architectural things like undocumented MSRs. And to sum those things up again, I'd say we can see those things, they scale a little bit better than PhD students, at least like 3,000 of them. And they're also extensible. So once you've built such a tool, you can maybe input some new seeds into Transynther, and then you can come up with even more variants. They're also versatile. We can just execute them on a new CPU instead of giving that out to a new PhD student.
Yes, and as you now will all travel home at some point, our tools are open source, and you can download that before you do it. So if you're sitting on a train, in a bus, not if you're driving a car, then you can already start using these tools, fuzz around, and maybe you find the next cool vulnerabilities in a CPU. So they're quite easy to use, so maybe you find something just on your way home. What would be a great ending for a conference, right? So these tools are still in the beginning. You've seen they are very, very easy, and we expect to have more complex tools in the future. But even these simple tools already allow to find new and unknown attack variants, can be used for regression testing, and can be extended. So despite the limitations we still have, it's already a great start, and we have good tools that are already playing a role in CPU research because, well, we can automate many things that we had to do manually in the past. So that ends our talk. Thanks for listening. I know it's already late, it's the second day, it's the end. But I hope you still took something away from that, and you will be playing around, and we see some new cool vulnerabilities that you can detect with our tools.